Hello all, welcome to my channel. I'm ready with a new video. In this video, we will look uh, how Flink SQL can be optimized. Although it says Flink SQL, the rules applies to all the table APIs. So let's get started. So Flink, before we start to explore the settings that we can use or leverage to optimize the Flink application, uh, first we have to understand how a Flink job executes a SQL query or how it translates that SQL or a table API into an executable component. So it starts with a SQL. So we have a SQL that gets parsed into different SQL nodes. Then from those SQL nodes, we create a logical plan. And while creating that logical plan, we do leverage the catalog to identify or resolve the references that are present on that particular SQL node. Because this SQL node is just a text to find out what does that text mean. We use this catalog, and once the logical plan is created, the optimizer creates an execution plan for using that particular logical plan. And execution plan generates code for each of the transformation. And then we have a job graph, which is nothing but an list of transformations with directed edges. And there is a one difference between Flink and Spark's DAG flow is that Spark DAG are acyclic, where this one, the Flink flow graph is not acyclic, it can be cyclic as well. And once the job graph is calculated, then that job graph is split into smaller tasks, and then each task is executed on the Flink cluster. So that's how this SQL uh, gets a normal SQL gets translated into an executable code, and it is run on the task slots. Uh, there are certain rules which are optimized, which are applied to optimize the query that is running. There are certain defined ones, like common ones are mentioned in here, like filter push down, the projection put down, partition push down, dynamic partition filtering, limit push down. So there are a lot of push down. If you see, that means that these push down basically means that when the Flink is reading or consuming from the source itself, then and there itself we apply the filters or whatever projection or partition that needs to be pushed down. So that keeps on happening. It also uses some other technologies, strategies like join reordering, replace minus with anti-join. So those things are there, and so that is something which we can see. So if we want to see the full list, we can look into the Flink code and find out whatever other optimization rules are there. And so once we are doing this, we have multiple options. Options in a sense, uh, what are the things that affect this flow, like which rules will be applied and which rules will not be applied. That is defined based on this. So this was the actual like the drag is break up into this logical plan, batch physical batch plan and everything, and then execution plan is there. So in between this, if you see, there are certain things which are mentioned, like for example, the rules are applied at here: cost based model, rule based optimization, cost based optimization, a metadata handler. So there are different things which are part of this calcite optimizer. And the external factors which are affecting this DAG optimizer, if you see the whole box, is a logical plan. Then we have Flink configuration, we have constraints like primary key, and then stats which are available for the in the batch mode, and hints if it is given in the query itself. So these things are actual components which or settings, or what do you call, knobs, which we can leverage to tune the DAG optimization part. uh, Flink configuration, many optimizer related settings can be adjusted in the Flink conf itself. Schema design plays a very important role. So in schema design, when we say if we don't have the right schema and the data type is coming, so we will have to do a lot of what you call upcasting, downcasting, or converting from one data type to another data type. So that schema design is also very important to to take note of hints. This is very common strategy that we use to affect how the planner is trying to execute the code. The reason for that is that this we might be aware of the systems that we want to use explicitly from our end, and for example, we might be knowing that okay, the table on the right side might be broadcastable, or table on the sorry, left side can be queried better if we create a hash out of it. So those things, if we are already aware, we can provide those hints. So this is the way to provide an hint in SQL. So it starts with a backslash and then star, and ends with a slash. Sorry, ends with a star and a backslash. And in between, we give a plus sign to mention that okay, this is a hint. So, for example, this plus options lookup table setting which is there. This simply means is let's say let's talk about this one. So what does this mean is that whenever the source data will be loaded, for example, let's say we are reading from a database and we are trying to perform a lookup. Let's say so instead of every time when a new batch or new set of event comes, every time instead of making this call to the DB, we can decide, we can say that okay, this table that you are seeing on the whatever is so in a stream to stream, John, what happens, one is a lookup, one is a probe, so probe side and the lookup side. So the lookup, we can say that okay, instead of making a call to every time and get the full data, we can simply say that okay, do a lookup cache and do a full cache of that. So that, what does this mean will that the source data will be loaded into memory and cached, and subsequent lookups operations that will happen will be performed against this in-memory cache rather than making the call again and again. So this is one. For example, then again we have a lookup prevails. So this says that okay, which side of the join becomes a lookup. So let's say we are saying that okay, T2 is our lookup table, and this sync true means it is simply means that it explicitly instructs Flink to use a synchronous lookup strategy for the join with table 2. So this is what does this hint tell. Then we have this broadcast, shuffle hash, shuffle merge, or nested loop. So these are join hints that we provide while doing a join in batch mode. And with this, we can define that okay, what type of join strategy that will be taken. Then we have dynamic table options as well. So dynamic table options are a way for us to provide or override the the plan that was already there, or we can say it affects the plan. Sorry, it affects overrides the things that which we are set at the, let's say, conf level. Uh, Take an example of, let's say, this is the way we define in dynamic table options. So we say options and provide the key and the value, or the list of values that we can provide. So in this case, for example, one is that for a particular table, let's say we are trying to do something like we want to set this parallelism for that particular table as 4, and read mode of that as a batch. So this option we can let's say we are reading a CSV file and we want to ignore parse errors, that is set to true. So this is something which we can do at runtime, and if it is there present in the configuration, that will get overridden. So that's what this means. Then we have other options as well. For example, let's say this is one SQL. And let's say this is one SQL which says select star from Kafka table 1, joining Kafka table 2 on this, and then we are inserting into a Kafka table 1. So this if we say instead of setting, let's say if we set a conf level, this applies to all, but here we can say that for this Kafka table 1, use the mode as earliest offset, while at for Kafka table 2 we can select to use from certain offset. So that can be one approach. So that this will give us two different settings for the tables which are running. So this allows more granular control on the configurations that we are, or optimizations that we are trying to do. Then this, for example, for the insert one, Kafka table one, again we are saying that okay, the partitioner for this sync should be round robin rather than, let's say, a hash based approach. So yeah, these are certain things that we can provide. Then there's another hint which is called the TTL. So the TTL is something which allows us to reduce the amount of state that is getting generated. Like for example, in this example, we are saying that instead of storing, let's say the state TTL was set to 7 days at in general, and what we are doing is we are saying that okay, we don't need 7 days TTL for orders and line item table. What we are simply saying is that okay, for the orders table, 3-day TTL is fine, while the line item there is only 1 day TTL is good enough. So this way we can actually improve state size very in a very good fashion. So these things are something which we can use to provide configurations in Flink, which allows jobs to run faster and faster, or not faster, at least, but in a performant manner. So that those are the things that we have discussed. There are certain optimizations which Flink does it automatically. We don't have to tell that. And one example can be operator and slot chaining. So what happens is that if we say in general, if we didn't have operator chaining, what would have happened is that we would have three slots that we would be consuming, one for source, one for map, and one for the sync one. And the task manager, what it does, one is that they will so first optimization that they do is that they run it on one single thread. And what they do even better is that because it is one thread, so it becomes only one task slot, and then in one task slot itself they chain the operation, so the amount of shuffle data that is going is also getting reduced because it's tightly mapped, and they can create a chained operation very well. So that's where this operator and slot chaining helps us in making reducing the number of slots that is needed to run a particular operator. Plus Flink also is able to share the slots between the subtasks from the same job. So for example, if we have one job, and in that job we have, let's say, operators, and each operator has certain subtasks. So what Flink says is that the subtasks or the task from the same subtask can be placed into slot which is not of this particular subtask but of a different subtask but of the same job. So and that helps in reducing the number of slots needed there as well. So this is something which Flink does out of the box. We don't have to do any change in there. And so that is one chaining the operators in running in the same thread is something as an optimization that we have. Then Flink also has an optimization called reuse subplan. So what this basically means is that if when we have written a SQL and the job is running, Flink identifies which are the jobs, which are the plan that it had generated can be reused rather than being calculated again. For example, in this case, we are creating a temporary view saying that okay, select star from this table where a is greater than 0, and then if we insert into B1, V like this, and then we have an insert into V where B is less than 0. So we have two different plans. But because we have this view and the when we create, so instead of creating two DAGs like one from select table where to the sync 1 and other to the sync 2, what it does, it reuse this select table plan. It has been reused, and then we do this sync conversion because this plan is we are saying select from V itself, so only one time this view is created, not created twice. Only the split that happens is at the sync level where this filter is applied extra. So we are just reusing the plan, uh, the subplan that was generated. The subplan being here is the creation of the temporary view. So this way we can help reduce the amount of aggregation or amount of work that Flink is doing. Then we have certain other things that we can use in here is certain other cases where we can use optimizations. So there are common SQL patterns, and we will see how it is optimized by Flink. So one common SQL pattern, sorry, few common SQL patterns are aggregation, joins, deduplication, top n, and pattern matching. So let's see how Flink optimizes, or we have what are the options that we have to optimize a aggregate operation. So one is optimizing the group aggregate using mini batch. So what does this mini batch do is it will reduce the state access. What it does it that okay, instead of creating the aggregation, it does the aggregation in mini batches, and so the input records are first put into buffer and then triggers the aggregation operation after the buffer is full. The moment the buffer is full, that aggregation is happens, and so the amount of data that needs to actually go into the operator again and again is lower. And in case of mini batch, so when batch is turned on, that means that freshness of data will be affected because we have a buffer, but it does reduce the amount of aggregations that has to be performed later on. So because we are doing as smaller work as possible, that allows the total resource requirement of the Flink job go down. But yes, as I mentioned, because there is a buffer involved, so some time is spent in there, and then hence the latency will be there. But if we choose the batch size correctly, that latency will be very significantly less compared to the cost, the benefit that it will bring out of not using the real-time streaming mode, and the mini batch will help us in reduce the storage needed. In case of so we have another approach as well for aggregation improvement. One this was for mini batch. The other one is doing a local global aggregation. So what does it mean is that the whole operation will be split into two phases, and one phase does the local aggregation, and then like the the stage is defined by a shuffle operation. So before shuffle operation, everything will be shuffled locally. Sorry, everything will be aggregated locally, and then the aggregation of that aggregations will be created as an output, the final output. So that's why, and then see if there are two phase strategy in here. So one phase, that the local one, and then the global one. So that's why it is called two phase. So if we enable this, we can reduce the number of states needed to maintain in the actual operation. And also this is only we can do for things which are commutative, in a sense that can be aggregated or can be merged. For example, we can do sum of two things let's say we have a local sum, so the global sum becomes summation of the local sums, right? And max also is at local max, and the max of all the local max also gives us the total global max. Count is also that one operation we can do. But for example, if you want to do distinct, we can't do a distinct because the local aggregation, local distinct will not combine and give you a total distinct, because we need a combination from everywhere to find out whether the thing is distinct or not. So those operations we cannot do with two phase option. There is another approach where we can do an incremental aggregation. So that is also one. Means the incremental aggregation will help us. This is already enabled. This also helps us in optimizing the resource requirement of the job. Then we have optimizing the group aggregation when we are doing a distinct. So distinct, what this feature allows us to do is when we are trying to, let's say, do a distinct and then count something, so we can split this into two phases, and each phase works on its own. So for example, it tells the optimizer whether to split the distinct aggregation, such as we have, let's say, count of distinct sub column or sum of distinct sub column, into two level aggregation process. The distinct aggregation can suffer from data skew, and that's where a few means data skew is where a few key distinct keys have a significantly higher number of records, leading to performance bottlenecks. So this optimization actually tries to distribute the workload more evenly, because we are splitting it into two part then not two parts, but splitting into number of buckets. So that's why this split bucket number is there. So what we do is we perform the distinct aggregation in locally within the buckets, and then we combine it at the top. So this is the split distinct optimization. Then we have aggregate with filter syntaxes. Flink does a rewrite of our job. Let's say if we are writing a case when statement, for example, let's say this is the statement which says that, okay, we are counting we are case when is wireless is set to Y, then we say visitor ID, else we say null, and then we are counting the number of distinct what you call distinct visitor ID. So this way is one approach of saying. So when this Flink sees this, it can rewrite this query into uh, aggregation with a filter syntax. So in rather than doing this, as you now, if you see, it says count distinct visitor ID as UB1, count distinct visitor ID, and the filter that gets applied is where wireless is as UB2. So that is something some optimization that's performed by Flink. So this rewrite is uh, distinct function can be this way. If we write the filter is also the filter is applied, and hence it will reduce the read and write operations on the state of the data. So that is one other optimization that we do. Then the other set of optimization or the pattern is on the join side. So Flink offers some join alternatives which we can use. So there are mainly interval join, temporal join, lookup join, window join. Uh, to understand it, what happens in interval join, the state will only store the date within that interval and the expired state will be cleared. So that's what, so what we say, select star from table 1. Let's say this is table 1 and then we have table 2 and then we are joining, and what we are saying is the proc time of T1 should be greater than the proc time of T2 minus interval of 5 seconds. So we are only keeping the state of the last 5 minutes, 5-second interval. So that doesn't mean 5 seconds, it can be 5 minutes as well. But yes, that's what it does. It will create intervals on the both side and keep on expiring the records which are not matching in that interval. Then we have a window join where we are creating a window start and end, and then based on that only we are joining that particular streams. So the state will only store the data within the window that we have set, and then expired states will be cleared. So that's where these things are all strategies that are used to expire the state that is needed for the application. So one is, as I mentioned, the one was where we are expiring the states based on what condition decides what kind of join we are using. So for example, here the states were expired based on the time because it was interval. Here the in window we have the state getting expired because we have defined the window, and in case of regular join, there is the state is not cleared as frequently as it is. In case of lookup, we do the clearance of state. So in lookup join, there is no state management per se. So that is not getting cleared. So that is fine. So this is sort in detail what each of the join does and how it performs. So we say that in interval join we define a time constraint where clause to bound the time on both the sides to a specific interval using a between predicate. That's what we do. Uh, so and in temporal join we are using the Flink's syntax for system time as of to perform this operation. So this will also reduce the state that is there. Then look in the lookup join requires one table to have a processing time attribute and the other table to be backed by a lookup source connector like a JDBC connector. If it is available, then the lookup join works. And lookup join also requires an equality join predicate based on the primary key to find the lookup join. So if we see if we have these criteria fulfilled, we can leverage lookup join. So we have different modes available in lookup join. For example, here what we are saying is that this was the table, this was a table join that was happening, and we are giving a hint that okay, lookup add a lookup join to this, and the lookup table is table T2 and mode is async. In this case we have output mode of allow unordered that we have set, and then we also have an output mode we can set allowed the mode is to be ordered. So that are two different options which are available in the lookup mode. uh, Lateral join again, lateral join in Flink SQL is a type of join that allows us to apply a table valued function to each of the row of a table and generate additional rows based on the function's output. And lateral joins are useful when scenarios when we need to split a column into multiple rows. So a kind of an explode that we are trying to do. So that scenario we can use to generate to use the lateral join. For example, if you see here this lateral join, so we are doing a lateral join on this. So the syntax for this is to pass the lateral. This is a good blog that good picture that I got it from. I think the source is Getting Data, so they have published a good uh, summary of different joins that are present. I recommend you to go and check out that blog, and it helps you to understand what attribute of certain things is available in each type of join, and work our way around it. So now, six main factors that improve the join performance is avoiding duplicate computation, reducing the invalid data, solving the data skew. So this we have seen as of now. We were doing this only, right? Improve operator throughput, all already being done by Flink. Reducing the state access, that's what we were doing, streaming based on the different join types that we have seen. Reducing the state size, again we saw how providing the right window or right interval will help in reducing the amount of state that is needed. So those things are there. And then we have some shuffle optimizations. We can also leverage external shuffle. For example, Scalabon supports external shuffle in Flink as well. Optimizing deduplication. So deduplication has many options that we can use. We can duplicate and keep the first row, or we can deduplicate and keep the last row. So for example, this example, uh, for the first use case, like keeping the first row, we just order by proc time in the ascending order, and then we order by the row time in the descending order, and then select the last row. Select the row number one, which becomes the last row in the event. So there are few deduplication techniques that we can use. And then there's just another set of problem, which is generally optimizing the top end problems, which is there like, so we have options of choosing append rank, update fast rank, and perform no ranking altogether. So these are certain SQL time, other options are there for the top n records. And how do we optimize that is we can include a time field in partition by, and then process the partitions, or do the transformations in the those partitions in parallel. And we can use built-in functions and the user-defined functions, and avoid using regular expressions. To in this case will help us in optimizing the top n records. So the other thing is to adjust the parallelism of our SQL jobs according to the Kafka topic source. So that is another optimization that we should be focused up. Let's say if our source topic has four partitions, so we should be at least using parallelism of four in our Flink application, or it we should be multiple of that. Uh, so that is there. Then handling of skew, we can do an MD5 hash and then create a primary table of that, and then uh, uh, the value of that will fail in certain ranges, and that's we are regardless of the primary key type that we have. So that will help in handling the skew. So this is one approach that we can take. And certain things that we can pass as an memory flags. For example, heap. If we are using too much of heap, it will cause heap OM, and then if we want to update the JVM setting, we can pass it as an XMXX. Metaspace OM, if we are getting, we can increase the metaspace size. If we are getting direct memory OM, we can increase the direct OM. And if it is failing due to task of it, we will get an OM killed error. So there are different reasons why certain errors will come, and we can pass JVM flags to work around those optimization, or those challenges which are there, like whatever error we are seeing. So this is it. I hope you like this video. If you have liked this, do share and help it reach more audience. Uh, Thanks for your time. Have a nice day.